What if I told you the key to understanding economic crashes and supply chain chaos isn't buried in some textbook, but it's actually in the schematics of an electrical circuit? Today, we're going to see what happens when you stop looking at the economy as just static numbers and start seeing it for what it is, a living, breathing system of signals. You see, economics often gives us a snapshot of the world, kind of like the circular flow diagram. It shows how all the pieces connect, sure, but it's frozen in time, in a perfect balanced state they call equilibrium. But what if the economy is less like a photograph and more like a movie? Well, that's the engineering view, a world of dynamic signals, constantly flowing and changing over time, just like this wave. And that right there, that's the puzzle we're going to solve together today. By sticking to these static, frozen models, what are we missing? What hidden rhythms, what unseen vulnerabilities are lying just beneath the surface? Let's find out what happens when we start treating the economy like the living, dynamic system it truly is. To get a signal, you need movement. And for movement, well, you need a force. In economics, that force is incentive. You know, the desire for profit, the fear of loss, the need to buy something. Without these forces pushing and pulling, the economy would be perfectly still, and we'd have no signal to analyze in the first place. So, a team of engineers decided to just build it. They created an economic model that behaves just like an electrical circuit. In their model, demand has inertia, meaning it resists sudden changes, just like a heavy object. In things like inventory or your savings account, they act like capacitors, storing up energy to absorb shocks. This whole setup lets them do something really fascinating. Hit the system with a jolt and watch what really happens. They used their model to simulate the COVID demand shock, and what they saw was this incredible chain reaction. First, households just stopped spending. So in response, firms cut back on production and stop borrowing. This, of course, leads to lower wages, which prompts the government to step in with subsidies. But here's the twist. With everything closed, that money has nowhere to go, so it just floods into savings accounts. And this created a massive problem for the banks. All of a sudden, their income from loans plummeted, while the interest they had to pay out on all those new savings deposits just skyrocketed. The result? Their net interest income, their profit, was absolutely crushed, as you can see clear as day in this chart. And crucially, watching this whole thing unfold over time showed that the economy doesn't just jump from one perfectly balanced state to another. No way. It produces real signals, full of waves, fluctuations, and hidden cycles that traditional static models just completely miss. So how do we make sense of all these overlapping cycles? Well, engineers have this amazing tool for this called the Fourier transform. Now, I know that sounds super intimidating, but the core idea is surprisingly simple, especially when we look at it through the lens of something we can all understand: farming. Okay, let's dive into this. The math on the screen might look a little complicated, but its purpose is actually really elegant. The Fourier transform is basically like a prism for signals. It takes a complex, messy wave and breaks it down into the simple, individual cycles it's made of. To really get how it works, let's just forget the formula for a minute and talk about farming. Imagine a farmer's year as a four-part cycle. Now, two of these parts are tangible actions we could plot on a simple number line: harvest, a positive gain, and plant, a negative cost. But what about the other two parts, protecting the land and preparing for the harvest? These are just as crucial, right? But they aren't about gaining or losing something tangible right now. They exist on a whole other dimension, what mathematicians call the imaginary axis. And suddenly, the term imaginary number just seems like a terrible name for it. It's not imaginary at all. It's a way to describe a part of a cycle that is absolutely real, the parts that involve preparing and protecting, not just giving and taking. As the quote says, it's as real as anything. And this is the key insight. The economy is just like this, but with thousands of cycles all spinning at once. The imaginary phases of preparing and protecting, well, those are things like R&D, long-term infrastructure planning, or saving up for a big investment. They don't generate immediate profit, but they are absolutely essential for future growth. You've got the annual rhythm of agriculture, the faster pulse of consumer credit, the ebb and flow of inventory, and the long, slow waves of business cycles. All these individual signals layer on top of each other to create the complex, messy signal of our economy. All right, so now that we can break down the economy into its component cycles, let's add another layer. What about the value of things over time?
For this, we're going to turn to another engineering powerhouse, the Laplace transform, and it's going to help us unlock one of the most fundamental ideas in all of finance. The core idea here is present value, and it's simple. Money you got a year from now is worth less to you than the same amount of money in your hand today. Why? Well, because you could invest the money you have today and earn interest on it. It's as simple as that. This process of working backward to figure out what future money is worth today is called discounting. So, as you can see on this timeline, that promise of $100 in 5 years might only be worth $78 to you right this second. So what is the Laplace transform? Think of it as a superpowered present value calculator. But instead of just calculating the value at one specific discount rate, it does it for every possible discount rate all at the same time. It's like a prism for financial value, breaking it down into a whole spectrum of possibilities. And this is where it gets really, really cool. This slide shows how a standard engineering lookup table becomes this powerful financial decoder. A single payment today? The math is simple. Its value is 1. It doesn't care about any discount rate. A stream of payments that goes on forever, like certain types of bonds, its value is just 1 divided by S, the discount rate. This table is basically a Rosetta Stone, translating the language of abstract math directly into the reality of finance. So what's the point of all this? I mean, it's not just some cool academic exercise. This new way of seeing the economy as a system of signals can help us solve very real, very painful problems. Case in point, the fragile, chaotic supply chains that we all got to know so well a little while ago. We can actually model a supply chain just like an electrical circuit. Producers making things in batches create a bunch of high-frequency noise. But inventory and wholesalers, they act like capacitors and filters, smoothing out that volatility so that the customer at the end of the line receives a stable, predictable flow of goods. During the pandemic, many supply chains experienced what was, at the very beginning, a relatively small shock at the customer end. A dip in demand, yeah, but not a catastrophic one. But that small dip didn't stay small. Oh no. As the signal traveled up the supply chain, from the retailer to the wholesaler to the manufacturer, each layer overreacted, amplifying the distortion. This created a chaotic, whip-like reaction, the bullwhip effect, where the final response from the supplier was massively, wildly out of proportion to that tiny initial change in demand. From an engineering perspective, the cause is crystal clear: resonance. Every system, whether it's a bridge or a supply chain, has a natural frequency. And when a shock hits at that exact frequency, the system doesn't dampen it, it resonates with it, wildly amplifying the signal until the entire chain is just shaking itself apart. By understanding the economy as a system of signals, we can actually design better filters, smarter inventory management, better contracts, to prevent this chaos from happening. And this leaves us with a final thought to ponder. If this engineering lens can so clearly decode the hidden dynamics of the economy, what other complex systems, from social networks to ecosystems, are we failing to see clearly?